Okay, so what we have done till now in linear regression, understanding of linear regression, hypothesis function, then understanding of linear regression cost function, then how to find the model parameters using gradient descent method. So gradient descent is one of the optimization method, which is very popular and which is very common in many algorithms. In some of the algorithms, a slight variance of gradient descent is used, but the gradient descent is a base for all the for a lot of algorithms optimization. And why we call it optimization? Because this is used to optimize the model parameters. What is our goal is to get the best values of the model parameters, so that using those best values of model parameters, we can get our accurate predictions. With linear regression, we also have other solution known as a closed solutions or sometimes analytical solutions, where we can find the values of these parameters directly using one simple formula. So this is what I had shown in the last class. 1 minute. Am I audible?
Yes. Yes.
Yes, ma'am.
Yes, ma'am.
Looks like my screen got
Yes,
hanged.
ma'am.
Yeah, okay. My screen got hanged. Yeah, okay. The screen was not moving. Mhm. I think it looks like PowerPoint is creating a problem. Yeah, so this derivation was just to know how we are arriving this formula, where X transpose X inverse into X transpose into Y. Now, what is X in this case? Yes. Am I audible?
Yes, ma'am.
Yeah, what is X in this case? Now you can speak because you can unmute yourself. So I don't have to switch between chat and here.
M by N matrix of parameters.
Sorry?
M by N matrix of training examples like x1, x2, xn.
Yeah.
Features, access feature.
Yeah, features, correct. So this is the hypothesis function of linear regression. It is thetas multiplied by features. But what we are doing here, we are taking individual training examples, features, multiplied by their corresponding weights, and then we are summing them together. We want to vectorize this operation. So we are creating vectors. So theta is a vector of all the coefficients. Now these are the coefficients for features. So one feature, one coefficient. We have D features total. So we have D corresponding coefficients. Those are parameters we can call it. You can call it coefficients or the weights of the features. This weights will remain same for all training examples. It won't change. But when we have features for one training examples, we want to combine them together in a matrix form. So the capital X is, we have created this capital X, which consists of all the features of all the training examples together. So rather than treating each training example and each feature separately, summing them, multiplying with each feature with its corresponding weight, and then summing them together, we are performing this using the matrix computation. So that we need to first convert everything into vector and matrices. So that's what we have done here. X is a feature matrix of all the training examples, and Y is their corresponding target value converted in the form of the vector. So here, when you see the vector length of Y, it is N. So what is this N is here? Are there number of features or number of training examples?
Training example.
Training example. So now you are clear with this. Dn is just a variable that we are using it. Some slide in some book, you will see a different example, different notations, variables used. But here it should be clear when you look at it, what will be the vector length of Y? It should be equivalent to number of training examples. And what should be the vector length of theta? Yes. D is just a variable is given. Yeah, D.
Number of features.
Number of features, yes. Dimensions and features both are same. So number of dimensions, okay, you can say like that, because when we talk in terms of vectors, we talk in terms of dimensions. But yeah, in terms of our training data set, they're nothing but a number of features. In a very simple language, they are the number of columns.
One
Yes.
question, ma'am. So,
Huh.
like in the gradient descent, we learned about mini batch and batch, and here we are
Huh.
taking all the training examples as the feature matrix.
Yes.
So, is it possible to also break it down into batches, or it should always be all the training example as a single feature matrix?
Yeah, single feature matrix. Because there's no iterative solution over here. This is simple a formula-based solution. So in the formula-based solution, we can like more scientific word, you can give it as an analytical solution. So formula-based solution, you have to put everything together. So the drawback of this is what, even though we have this direct formula-based solution, you can easily write this formula in NumPy. Matrix multiplication, matrix inverse, and matrix transpose, 4-5 line of code, and it can compute it very fast. But the problem comes when the number of features are very large and the number of training examples are very large. In that case, matrix computation of so many, such a huge matrix and matrices will be a problem. So again, even if we have a closed form solution, for a larger training data set size, it is always good to use the gradient descent. So if you look at the sklearn and such library, there it's a general interface given. Your training data set size could be smaller, larger. So gradient descent is the solution which can be used. But yes, when you are doing coding from the scratch, not using any APIs, it is up to you. You can decide depending upon your training data set size, or you can just work around, try and see how much time difference it is coming. Okay, so this is what I had shown one example. Here we are ending all the discussion about the linear regression, the main part, the main algorithm. Now we will see a general concept of linear basis function models. This basis function is applicable even for the logistic regression or any such algorithms. Now, what is the fundamental over here? Say we have a green curve, which is the original curve with which data is generated. You can think about that you are creating a signal, applying a sinusoidal signal. So you're creating the waves using sinusoidal signals. So the function, the mathematical function which is used to generate the data points follows this green curve. It's a sine function. And we have been given a certain data points, blue data points, which you can clearly see it follows this sine function. We have been given only the sample. Okay, and that is our training data set data points, and that's a blue curve. And I want to say we cannot pass a single line from this blue curve, blue data points. You can clearly see this kind of a data set where we cannot pass a line or a hyperplane through most of the points. What happens if we try to pass a line? Can you pass a single line to any of this point? And if we try to fit a line to this points, the error would be very high. There are many points which are far deviating from the line. So such kind of data set, we call it non-linearly separable data, where we cannot linearly I mean, here we are not talking about, okay, I should write non-linearly separable data, or in case of a regression, I should write non-linear data set. Separable is a word that we generally use for a classification task. This is a regression task. So use a simple word, non-linear data for a regression task. Non-linear is a very simple word that all points, they do not lie on a single line. In that case, we would like to fit a curve. How can we use this curve fitting? So we call this as a curve fitting using the regression model. So example, this is an example of a polynomial curve fitting. You can clearly see this is the polynomial curve of some degree. Polynomial, in general, we can write down this polynomial function with this kind of mathematical expression, where you can see we are talking about x is our feature. Then we are taking a various degrees of this x. And I can write down this in a shorter notation, wj x rest to j. So in linear regression, what was the hypothesis function? W into x. And obviously when I write this, we are just doing it for all the training examples. And then say just one feature and all training examples, we do this. Here, rather than x, we are replacing x with a polynomial polynomial degree of x. So why are we doing all these things? What if our linear model is not good? Because we have a non-linear data. If our data set has got inherently non-linear characteristics, then we cannot, I mean, if we try to fit a linear model, whether it's a regression problem or it's a classification problem, we won't get good results. We won't get good accuracy. So we can create this more complicated model by defining input variables that are combinations of x. I think one of some of this I had explained some past classes as well. So here what we have done, what combination is created here? Rather than x, we have created some polynomial of x. You can define, you want to have up to degree 2, degree 3. So if it is just degree 2, it will be W0, W1x plus W2 x square. So this is m is equal to 2. So likewise, we can define, that's the one example of basis function, the polynomial function. Now, how this and the name given to this regression is a polynomial regression. We studied linear regression. Now we are studying polynomial regression. What is the effect of this degree? So say it's a degree 0. Degree 0, that means it's a straight line. And you can see green is the expected curve that we should get. And if I define a degree 0, so you can say here in this equation, m is 0. Degree 0, that means you will get only biased term. Even x is to 0. Degree is 0. So this term will be 1. So there are no features. No features and their coefficients. Only W0, which is a biased term, will exist. So the curve will be something like this. Whatever is a bias value, depending upon that, the curve will be it will be a straight line. Now, is this acceptable when I have the blue data points and then we take a degree 0 polynomial and we get this red line? Is this model acceptable?
No.
Okay, then we change the degree to 1. So we are still getting a line. Degree 1 polynomial is what? W0 plus W1x. So still it's a straight line. So is this line, degree 1, is it acceptable? Red line?
No.
Now look at degree 3 and degree 9. Just randomly picked up some number and we are getting this red curve. Both the cases, 3 and 9. Which one is acceptable? Or I should say, which ones are acceptable?
Temporary.
M3.
9.
3, 9, or both, or only 3. Or only
9, madam.
Only
9.
9.
Passing through all points.
Okay, fine. This is a training data point. Now let me introduce one test data point somewhere. It is somewhere here. After last 4 points. Okay, somewhere here I will introduce a test data point. I would just want very accurate point. Okay, this is a good. This is a test data point. Blues are the train data point with which we train the model and we get the model. So say we have got this 2 model, m equal to 3, m equal to 9. That means I've got a mathematical expression with a degree 3 polynomial and a mathematical expression using a degree 9 polynomial. Training is done. Now I'm comparing this to model using the test data, and this is a test data point. Which one will give me the higher error among these two?
9.
9.
9.
I
9.
think m equal to 3 will be good because m equal to 9 is more overfitting the curve. I think.
Yes, yes. So here you can see this that for the new test data point 3, the error would be low compared to the other m equal to 9 model. This is what exactly we need to understand. Our test point.
We don't have to consider 0,
What is 0?
degree 0, first case.
No, it's a very simple model. See, during the training, you should try to get minimum error as much minimum possible. Among 0, 1 and 3 and 9, 3 and 9 both are giving minimum error. So now we have to do a comparison between 3 and 9. 0 and 1 is out of question. If a training error is high, your test error is never going to be low. Now, yeah, 3 training error is low, 9 training error is more low, or I can say 0 in this case, because all our curve is passing through all the data points. So what happens if a new test point comes, the error would be high in this case. So that's a generalization performance. Our end objective is that our model should work good in the real world. I mean to say in the when it sees any unseen data. And that's what when we deploy our model, the data that our model will come across is not seen during the training. So in every machine learning predictive problems, the more emphasis is on to increase the generalization performance. So even if with the m equal to 3, so third degree polynomial function, the training error would be a little higher than what we have in the rightmost graph, but its generalization performance would be better. So that's what we call it test error or the validation error. So we have to, after we have to choose between the models whether m equal to 3 or m equal to 9. The first intuition says that choose m equal to 9 because in that case error is 0. Training error is 0. But we should be concerned with the test error as well. So I'll talk about evaluation metric in a while. So this model is known as an overfitting model. So overfitting is again a very important concept in machine learning. But yeah, I'll talk about overfitting in detail.
Ma'am,
Yeah.
in case of linear new data point or to find the prediction for a new data point was simple a projection on the line. Here also we are simply drawing a projection of the new data point on the curve,
Yes.
or is it? Okay.
Yes, same way. So in general here, I'm explaining the concept of basis function. Our model is W transpose X in the form of vectorized form. Rather than X, in the previous case, we replaced it with W transpose, or I can write in this form Wj into X raised to J, some degree polynomial. So we can write this as a generalized function, 5 of X. Rather than X, we are replacing it with some transformation of X. In case of polynomial regression, we did a polynomial transformation of the features. So you can imagine just we have one feature X and we want to develop the machine learning model but that's not sufficient. So we can take this kind of a different polynomial of that feature, different degree of that feature, and we create many features. But polynomial is not just one way of transformation. We can do a lot of other transformation functions. Now you can use any mathematical expression as the linear basis function. Of course, every expression will have its limitations and advantages. So in a very simplest case, I can say that for a linear regression, this basis function is nothing but the feature itself. This is the case of linear regression. And we call it linear, still we call it linear basis function model, which is trying to fit a curve to the non-linear data. Why we call it linear? Because they are still linear in parameters. Now our hypothesis function will become non-linear in the input space, feature space. But still, as you can see, we are not touching this parameter. We are not transforming the parameter. So that's still linear in the parameters. That's the name, hence the name linear. Even though we are using this to predict the, or I can say to fit the data set, which is non-linear in nature. So as I said, we can have any such transformation. You can have log, any mathematical expression or polynomial expression, or we can have the interaction between two variables. We can multiply two variable. So any such mathematical expressions are possible, which can replace our x with some transformation function. We call it transformation function. In some of the algorithm, it is used as a kernel function. Kernel has got a specific name. So in SVM or on such, we use this as a kernel function. In case of our linear regression and logistic regression, we'll call it as a basis function. We are changing the basis. So in case of linear regression function, it is just the x. In case of a polynomial regression, it is x raised to j. You can have any other function. We can have log of x. Any such transformation is possible, then it becomes the basis function model. Few of such example is this polynomial basis function. We are replacing x with the polynomial, some power of x. This is just for understanding. You don't need to remember the formulas or more detail about it. But when you want to try anytime in your coding, you can try when you're using linear regression. And if it is not fitting your data set, you can try replacing the x with a different transformations. There are certain API modules are available in sklearn, but for a certain cases, you may have to write code on your own. This is known as a Gaussian basis function. This is the Gaussian function formula where mu is a mean and this is a standard deviation. So you will learn more about Gaussian distribution in Gaussian functions in your ISM class. So I'm not talking much about it. What is this Gaussian? Say this is some kind of mathematical transformation we have done and we are calling it as a Gaussian basis function. So rather than x, we are replacing by this function. We are calculating and replacing the x value, each of the feature value by this function. Similarly, we can have a sigmoidal basis function. So sigmoid is another mathematical expression. And this is symbol for a sigmoid, where x minus, again, this is mean and this is standard deviation. And what is a sigmoid function? 1 upon 1, I can say 1 upon 1 plus e raised to minus a. So this is a sigmoid of a function. Again, I'll come back to the sigmoid function when we start talking about logistic regression. So it's another function like logarithm, it's one function. Exponential is another function. Sigmoid is another function. So this is about the basis function, and it's a general base. Wherever we see x, we can do the transformation, and in that way, we can cater the non-linear data sets. Okay, so here I'm done with all linear regression. Now we'll talk about evaluation metrics. If you have any doubt till now.
So the definition of loss function doesn't change for any,
No,
no matter
No.
is it linear or polynomial, right?
no, it doesn't change. where we are simply replacing x with 5 of x, some transformation.
Yeah, so the formula which we evaluated during the last lecture, there also we just need to replace x with that representation of the function everywhere, right?
Yes, yes, yes.
Ma'am,
Okay.
here are we scaling the features? Like that.
That all will be applicable. See, whatever we do scaling
Hmm.
is we do before we apply to the machine learning model. And it is
No,
good
when-
to scale your features.
No, when we say we are applying a function of x,
Hmm.
does that mean we are scaling in?
No, that doesn't mean we are scaling it. We are transforming the feature value. Scaling is what you have two features of varying scale. Then you are
Hmm.
bringing them together in the same scale between 0 to 1 or minus 1 to 1. So that later on, whatever transformation that we do, that
Mhm.
scale doesn't dominate the prediction. So take number of bedrooms and the square feet. It's my housing price prediction problem. Number of bedrooms you will have up to 10 maximum, and square feet can go up to 10,000. So that's totally different. So that higher value, that square feet will dominate the prediction. Yes, for a certain algorithm, that dominance is not too much, but for a certain algorithm, it is a necessity to scale. That you will see, which are the distance-based algorithm in the future, KNN, K-means, like that. But it's a good practice to scale it before and bring everything into the same scale.
Got it. Thank you.
Now, I'll talk about this evaluation metrics. So till now, I'm only talking about trained data. We use the trained data for training the model. Training the model, that means we are learning the best value of the parameters. So we have been given the actual data set. In that, say we divide 80% data goes to the train. And say, for example, 20% goes to the test. Right now, let's hold on this validation part. So let's say we are dividing our data set into train and test. But yeah, there's something called validation will also come into picture, but I'll discuss this later. So 80% goes to the train, say for example, and 20 goes to the test. We want maximum data to go to the train data set. Now, depending upon of your data set size, if it is say just 1,000 data point, you may want to stick to 70-30 ratio. If you have a data point, say 10,000, okay, you can increase the training data and reduce the test data point. You have say 1 lakh data points, you can have 90-10 ratio. Just to check that whatever you have trained the model and whatever parameters you have found during the training, they are the good parameters and they will give you the good prediction over the unseen data point. But if you have said 10 lakh data points, you may consider this split up also, or sometimes you have 10 million or more so data point. In practice, you can also consider 98.2 or a 99.1%. So these are the general train test ratios possible. So say 80-20 or 70-30 we see for machine learning problems because we do not have such a huge data sets. But yes, for a deep learning problems, when we have data sets in millions, these are the common ratios. Now we are dividing into train and test. During the train, we consider loss function. For a regression problem, what metric we use for the loss function? We define a j of theta, some function we use there. You remember this, that expression? Mean square error. Yeah, the mean square error. So loss function is essentially error function, but there are many error functions possible. So which error function we use to calculate the loss and for the optimization mean square error? But we use that on the trained data set and then we trained it. Now comes the evaluation metric. So when we talk about evaluation metric, we have to do it on a test data set. And there are many evaluation metrics which we test of a model based on, and then we test on the model and then we get the statistics on those evaluation metrics. Mean square error I've already talked about. This is what we used in the loss function during the training. Root mean square error is just root of it, because sometimes this gives a very big number. So we just want to reduce the scale of that number. The other one is mean absolute error. Here we are taking actual minus prediction everywhere. In case of a square, we are squaring it. In case of absolute error, we are simply getting the absolute values. We just want a number. We don't want a sign, positive or a negative sign. Now, and there are other two more metrics, R square and adjusted R square, which I'll talk about in next one. So what will happen here? When to choose them? Code, sklearn gives support for all this evaluation metrics. In one line code, you get MSE value, MAE value. But the important question is when you try to explain this, your output to your business team, they don't understand all this technical, what is mean square error, what is mean absolute error, or you're making some decision based on this prediction. You have to justify your decision. Why are you making this decision? In that case, the evaluation metric of your model is important. Then obviously with your business knowledge, you will convert those evaluation metric to your business metric. So that's a totally business part of it. But you have to understand when to communicate MSE, when to communicate MAE, etc. So say this is just very simple example. These are the actual data points. In case 1, that is a model 1, you can say model 1 has predicted for the 2, the value predicted is 4. So 4, 6, 8, 10. Model 1 has predicted, and the model 2 has predicted 4, 6, 8, 10, 12. So we see that for rest of the 3 data points, both the model has predicted the same values. Only the last data point, say 8, model 1 has predicted 10 and model 2 has predicted 12. That means model 2 is deviating more from the actual values. And then when we calculate absolute errors and root mean square error in both the cases, you see in the first case, it is coming to both cases. In the second case, I mean, it's a second model, its root mean square error is coming higher. This shows that it's a simple maths. Here we are taking difference, absolute value of the difference. Here we are taking the square of the absolute square of the difference value. So the square will increase the number when we take a mathematical square of any number. In other words, your MSE will penalize your bad prediction too much. So this is a bad prediction. 10 and 12. 12 is much worse than the rest of the data point. Rest of the data points were deviating with a small number from the original one, the actual one. Last data point was deviating more from the actual data point. So that's a bad prediction. And your mean square error will penalize more to the bad prediction. Now think of a situation, you have an outlier. So if, see, this is my data point. This is the regression line. And we have some outlier here. So when we take the error, definitely for this outlier, error is going to be very high error. And then we take a square of that error. That means when you have a lot of outliers in the data set, then mean square error will go high because of these outliers. Your error metric should not show, your outliers should not dominate the error metric. Then we can use the mean absolute error. See, the practical scenario, you have to take care of this outlier before we start the prediction. Either remove the outlier or there are so many outlier detection techniques are available. The very simplest one is remove. Okay, let's build the model and try to find out the metric which is more robust to the outliers so that we can communicate correctly to the business team. So MAE, mean absolute error, could be the good option. But mean square error is the very popular error metric Only in certain cases, this mean absolute error is used for communication. So you can calculate everything. Then it is up to you that what to communicate to show that your model is performing good or bad. So in that case, MSE is still very popular. Whether you use MSE or root mean square, it doesn't matter. Root is just scaling down its value. Then we have something called percentage error, mean absolute percentage error. So you can say a formula is changed to so that we don't get any absolute values. I mean, any absolute numbers, but we get a relative number in terms of percentage. Maybe sometimes you want to communicate to your business team who doesn't understand like what is the unit of square error or absolute error. Let's talk in terms of percentage error. So in that case, you can use this percentage. You can calculate this mean MAPE and gives the output in terms of percentage. That my model is giving 70% correct answer or 80% correct predictions like that. So that's the another error metric. Okay, any doubt till now? Then I'll talk about R square and adjusted R square. What is this R square? Okay, there is some formula given for the R square, and sklearn has got a direct method. You can use it to give you the output, R square output. And if you just see the explanation of the formula, explained variation. Y hat is a predicted value, and Y bar is a mean value of the actual Y, mean of actual Y. So when we do this prediction minus mean, we call it explained variation. What do you mean by explained variation? The variation in the target, that is Y, which is explained by the regression model. So Y hat is the prediction which is being done by our regression model, which we have trained during the training. So it should not happen that the prediction are just by fluke coming out. In our regression model, the parameters do not have an effect on the prediction. Now, the unexplained variation is nothing but the error. This is actual minus prediction. And then we have a total variation, which is actual minus average, mean of actual. So this way, this unexplained, explained total is defined. Then we are summing. These are defined for one training example and sum of square. We take a square of all of these differences and then sum. So SS always stands for sum of square. That means we are taking all the training examples and we are summing their error. And then we have some formula for the R square. So important part is what? How do we interpret this R square value? First of all, for a good model, R square value should be high. R square value tells us that the variation that we are getting in the prediction is actually explained by our regression model. That means it is also known as, it measures the goodness of it. So we have got a model. We have got 10 features in that model. Then we have trained the model. We got 10 different parameters values for those 10 features. Now we use that model for a prediction and we are getting certain predictions. Say we are getting very accurate prediction. Not just by fluke coming up, by chance. So we also check the R square value. If R square value is also high, that means those features that our in data set are highly predictable, highly predictive features. So say this mileage and the car price. So whether this mileage is a good predictor of a car price, that or likewise we have so many features. The year of the car or the brand of the car, etc. Are they actually contributing to the prediction of a car price? That's what we want to find out. And why do we want to do that? It's okay when we have 5, 6, 8, 10 features. But when we have 50 features, when we have 100 features, having all the features in the model is costly. So we want to make sure that our features are good. Or say we got 5 features and we got some error value, evaluation, error metric. And then we are not happy, satisfied with that error value. So we will add the feature. Say, let's collect the data and add the feature. So we are adding some features. Addition of the feature is actually helping or not helping. That's another question. So here R square value will simply tell us the current set of features is a good fit for the model or not. Because if the features are a good fit, during the training, we will get a good fit of parameter values. But if the features are not, or I can say the features do not have a predictive power, then R-square value would be low. That means we have to go and change our data set, remove certain features, add new features, etc. We have to do. That's what is known as a goodness of fit of a regression model. Now, again, R-square has got some drawback. Take this example here on the right-hand side. Okay, 1 minute. I'll just take that down.
So a simple question. Here we are talking about regression model, and R is denoting that. R square is nothing but regression.
Coefficient.
Yeah.
No, it's not a regression coefficient. You are trying to relate with a statistic value of coefficient of correlation, R? No.
No.
No, okay. R square is, you can say it's just another error metric. Yes, it is related with the statistical coefficient of correlation, but let's not get into the statistics. For a machine learning understanding point of view, R square uses this formula to calculate some value and how you need to interpret that value. So higher the R square value, that means your models, the features that you have used for a prediction, they are good. So we known as goodness of fit. And it's very important criteria that it will tell us the features that we have used are good or not. If features doesn't have a predictive power, during the training, how much ever we try to get the best parameter value, features itself doesn't have a predictive power. So that's what we want to check with the R square.
Okay.
Now we have this adjusted R square because R we have a model 1 where we have one variable, that means our one feature and one output. Then we created another model where we created another variable, another feature. This is say feature 1, feature 2. What do you see, observe over here, how we have created another feature? Okay, these are the data points, x1, first data point, second, third, fourth, and 5. This is a 5 training example. And
Multiplying
from
to scalar.
Scalar. Yeah, 2, 3, 5, anything. Now, tell me, when we try to find the correlation, whether this will have any different effect on the prediction than what we have the original X feature. It's a simple scalar multiplication. So, whatever is a correlation between variable 1 and y, how much whatever scalar variance we create of variable 1, the correlation between variable 2 and y will not change. That means if a variable 1 is increasing, maybe the y value is 2. So whatever correlation is being captured or exists between variable 1 and y, same correlation exists between variable 2 and y. Then what is the use of variable 2? In other words, variable 2 will not contribute in the prediction because its correlation is same as a variable 1. That's what we call that when we are increasing feature, we need to check that increasing the features is actually increasing or improving the prediction. If not, that increasing feature is of no value. So you may find such features in your data set where the correlation is very high. So variable 1 and variable 2, indirectly, if I want to find the correlation between 1 and 2, can I say between 1 and 2 correlation is very high? Yes?
Yes.
Because it's simple multiplied by 2. When x1, when the variable 1 value will increase, variable 2 value will also increase. It's a directly proportionate. So such highly correlated features will not help us in improving the prediction. It will unnecessarily increase the cost in terms of computation, cost in terms of time. So our adjusted R-square value will help us to identify that. We have certain formula. So we are not interested here. We will not do any derivation how these formulas have come up. So what we are interested into? here in this case that the adding more feature is actually helping or not. You will encounter this situation many times in the practical implementation. So the drawback of R square is that it assumes that every feature helps in explaining the variation in the target. So R square assumes that every feature that you have in data set, they're equally contributing towards the prediction. R square will just tell you the collection of features are are a good fit for your prediction or not. It's a good fit model or not. But it won't able to distinguish between individual features' predictive power. So how will it help this adjusted R square? So you have taken one model, you're not happy with the some kind of evaluation metric. You take another model, increase the feature. Now that by increasing the feature, R square value will definitely increase, but you also will check the adjusted R square value. By increasing the number of features, is it actually increasing the predictive power or not? In that case, if it is not increasing, adjusted R square value will decrease. So that will able to help you that increasing the feature is not helping. The adjusted R square and R square is in that way is very, very important metric to know the goodness of fit of the model. Many times in the real applications, that's what you will use.
So
So again,
adjusted R,
yeah.
sorry, ma'am. So adjusted R square is also trying to find out the contribution of a feature towards the prediction, considering not all are equally contributing. Right?
Yes, yes. You may not get that equal contribution, what each individual feature is contributing. No, but you will only, so basically you can use it for a model comparison. Initial model, you did not get a good result. You increase the number of features, you got another model, but all that task is actually helping you or not. So that way you can use the adjusted R square.
So can we also find out or get the similar results by finding out the correlation between the features? I think we discussed this in one of the previous lectures.
Yeah, you can do that. You can do that. But
Simple thing.
you can do that. That's what we do analysis and before we start the prediction.
Right.
We do correlation analysis between every feature. But sometimes when you have 100 features, so how many correlation you need to check manually? 100 into 100, right?
Right. Right.
Between each pair of features, we have 50 features, 50 into 50.
Okay.
So this could be the easier way. It's just one line of
This
code.
can maybe this can narrow down our list of features which
No,
which
no,
we
no, no, no,
find
no, no.
correlation.
That it won't do. That it won't do. See,
Okay.
that's what. It won't do that. It won't tell you. It won't help you in feature selection. There's not a feature selection technique at all. Then you can use some feature selection technique, either correlation coefficient or there are more advanced feature importance of feature selection techniques are available in the beginning. Okay, this is what a model comparison. Specifically useful when you have 1 minute, when you have less number of features and you're trying to get more features by trying to get more data. So you can do it for a sample point and check rather than investing, trying to get more data is again a costly affair. So that way, or you have 2, 3 models you have done, you have got the data, 5 feature, 10 feature, 15 features, 3 models or 5, 6, 7, 3 models. You want to deploy again, while deployment also you want to reduce the footprint. More number of features, that means you are going to, footprint of that model is going to be increased. So a lot of consideration comes into picture when you actually deploy it. So that way it will help you to make a decision between the model selection. Yes. Anybody wanted to ask something?
Yeah, it got answered, madam. My
Okay.
question is like in R square
Yeah.
adjusted, we will go with the feature by.
Okay, so this is what I've simple heuristic written. Not necessarily this kind of thing will always work, but when you have a lot of outliers and you did a lot of outlier handling techniques before, but still your model has got outliers which you cannot get rid of. Maybe try concentrating and check the value of MAE and then scale independent metric in terms of percentage. Then you can use MAP. Then you want to know goodness of fit the model. Then R square, adjusted R square, both you can use. And then check for the model comparison. 5 features, 7 features, 9 features. So you've got 3 models. Compare them. Actually increasing these 7 features to 9 or 5 to 7. selection. Okay, so this were the evaluation metric, regression evaluation metric for any kind of algorithm. Linear regression, polynomial regression, then you will have SVM regression, decision tree regression. Evaluation metrics will not change because this is something that you do after the model training is done. We have a different algorithms only for the training part. So linear regression is one algorithm for a regression problem. Decision tree regression is another algorithm for a regression problem. Once the training is done, all of the algorithm, if it's a regression problem, whatever evaluation metric I have talked about till now, you can use it. For a classification problem, whichever algorithm you use, even all the advanced deep learning algorithm, the evaluation metrics will not change. So that we'll talk when I'll start the classification. Okay, so now we'll talk about overfitting and underfitting. So any doubt till now, or I'll etc., kitchen size, bedroom size, window size, etc. And then when we try to plot in a multi-dimensional plane, this is a simple example with one to all the points. Just now I had explained that that's not a good model because it won't give you a good generalization performance. So that way we have we are defining three different quality of fit. The leftmost model. See, the cross are our actual train. The middle one, that we are passing some curve, which is approximating all the data points. And in the third, we are passing a curve which is exactly passing through all the data points. So just now we have established this is a case of overfitting, that our model is overfitting the data set. The leftmost is underfitting. We call it underfitting. It's a very simple model. So during training only, if we are using a very simple model. So in this example, we are using a linear model to model this non-linear data set. But in the towards the right hand side, we are overdoing it by overfitting the data set. And the middle one is just right model. So you can say the left one is a say linear hypothesis function. The middle one say maybe a quadratic hypothesis function. And the last one is some higher degree polynomial regression hypothesis function. So which is overfitting. Overfitting case is also known as a high variance case. Now, what is the variance? That we have a different data set. Different data set will give a different kind of a prediction. And the prediction among different data sets will vary drastically. So overfitting case generally gives the high variance. So when we say that we have an overfitted model, overfitted the data set, we will generally this underfitting data case is known as a high bias. Now this bias, do not get confused with a W0 bias. High bias, that means high error. The training error would be very high if we are underfitting, our model is underfitting the data set. So we call it high bias. And when we have just right, that means there is a bias and variance trade-off. So ideally we want low bias and low variance.
So
But many times,
variance,
one minute. So many times it happens that we try to increase the, we try to decrease the bias. That means we try to decrease the error, but we are increasing the variance in that case. So here also you can take an example. Here from the left one, okay, it was high bias. So we came to the middle one, still bias is high. So we came to the last one. So we got a zero error, zero bias, but then we created a high variance, overfitting case. Then we are going back, the middle one. Even the low bias is okay because it is having a low variance. So that's the relation between underfitting, bias, overfitting, variance. And the just right model will have low bias and low variance. Yes.
Yeah, so the variance, we will consider the population or just the sample? If we
set, we generally sample. Okay, when you see the validation during the validation, the data sets are sampled. So we create a small samples of the entire data set, and then we train the model. In case of that validation concept, and I'll explain that. So, or in the other case, whenever we require that we need to do a sampling. When we do a sampling, we have a multiple smaller data set we create, and then we train the model, and then we observe that among the smaller data set, how much variance is observed in the prediction. So that is where the high variance will come into picture. So, or another example, if we change the training data set, definitely model is going to change. But within the training data set, we do sampling with replacement and do the smaller data set. So generally, this is observed when we do a validation and the k-fold cross validation. So again, that I'll explain in some future sessions. What is this k-fold cross validation? So high variance is a case where we have the multiple data sets, or I should say multiple samples from the one training data set created, but sampling with replacement. That's where it comes. Yeah. So yes, so when we have underfitting, like our model is learning too little for the true concept, features are not sufficient, too much bias, that means too much error in the model. So we have to do something. We are increasing the features, but then we have to, we have to be careful that we are not fitting the data too well. So many features we have increased, and that is fitting the data very well. So sometimes features are noisy, or so many features may be uncorrelated. So all those cases are overfitting. Easy to handle underfitting. If error is high, either you can change the model or you increase the number of features. But detecting overfitting is difficult and handling overfitting is difficult. So we have a special technique of handling overfitting. So overfitting happens when we have a very complex model. In case of a polynomial regression, when did we see overfitting is happening? Polynomial regression. Yes, in the beginning only I explained that.
Training error equal to almost 0.
No, that's okay. I just explained the polynomial regression when I started.
the degree was higher.
Yeah, degree was higher. So polynomial degree is higher. In that case, in case of a polynomial regression, we say overfitting was happening. So that is a general, we can call it a more complex model. In terms of features, if we have so many features, it's a complex model. So in other words, when we have too complex model, our loss function, during the training, if we try to achieve a zero loss function, zero cost or zero loss, then you should not actually aim for a zero loss function during the training. If that is the case during the training, then it will not generalize to a new example. And whenever you observe the loss is zero, you should say that you are overfitting the data set. So during the training, you should not continue the training, or there are different methods to avoid overfitting depending upon the algorithms. But yeah, we should not try for zero error. Otherwise, it's very intuitive. Okay, if you're getting a zero loss during the training, my prediction would be best. No, your prediction would be best only for those training examples. Unseen examples, this is a bad choice. And we have seen in case of that polynomial curve fitting problem. That's a mathematically, you should see that our this cost function should not go to zero. Now, how do we handle this overfitting? Size of a data set. So take more number of example, increase the data set size. One is so many features you have. That is causing a problem of overfitting. So many features, but the number of training examples are less. That's the ideal combination for a overfitting. So increase the number of data points. If possible, try to gather more data. So here n is the number of training examples. And here we have increased. So where we got 15 training example, same polynomial curve fitting problem with some polynomial degree, we got this red curve. The ideal is the green curve. We got a red curve. Now with the same polynomial degree, if we increase the number of data points, we will get this red curve, which is approximating the green curve. So even if we have a complex model, because sometimes simple model is giving you the high bias. So you have to take a complex model, but to reduce the overfitting, then increase the number of data points. Always there is a trade-off. You cannot get an ideal solution. When you say, okay, reduce the number of features, we may reduce the overfitting, but that will increase the bias, that will get into underfitting. So what is a solution? Find increase the number of training data points, retain the number of features. That means retain the complex model, but increase the data set size. That's one solution. So you see, there's a difference between lower order model in case of polynomial models and higher order model. Just 2 minutes, read this diagram, this graph. Validation set, just assume right now it's a test set. You see, in this left case, lower order model, the red one is a training. Training is, the error is very high. That means test error and the train error is approximately near to each other, but it doesn't matter because the training error itself is very high. You cannot accept this. Then in case we got with the complex model, higher order model, so training is low, but then you can clearly see that red curve and the blue curve. Blue curve is a test error. There's a huge gap between train and test error. Training error is low, but the test error is high. Again, not acceptable. So we increase the training set size. And you can see after this point, say some number, some 40,000, 50,000 data points, the difference between test and the train error is low. Train error is also low, and the gap between train and test error is also low. So that means training error low is the low bias model, and the test error is low, I can say low variance model. So training set size will help in reducing the overfitting. Now we have another way of handling overfitting. Early stop the training. Maybe we are too much overdoing the training. So we can have this kind of analysis. Epochs. Epochs is nothing but the gradient descent iterations. It is also known as epoch. One iteration, one epoch. 100 iteration, 200, 300. So likewise, you have the gradient descent iteration and the error. So during the implementation, this is what we can do. We can also calculate side by side what is RMSE. And you can check over here on the training set and test set, both will separately calculate RMSE. And after this point, see till this point, everything is fine. Our training error and the test error both are reducing. They are approximately near to each other. After say 250 epoch or probably here, say somewhere 270, 280 iterations, training error keeps on decreasing. That's good that's good, but test error keep on increasing. So this is a point where we want to stop training. And whatever parameter values we are taking, we should consider. So that's another way of handling, that you should not overtrain. Not always try to achieve the minimum possible train error. This way it will help us to when to stop. So again, this is one of the criteria. When should we stop the gradient descent iterations? You can say this is say one of the criteria that okay, when you achieve this many iteration and I see then another way is reducing the complexity of the model. That means reduce the degree, polynomial degree, or reduce the number of features. We have already talked about this. So in general, this is what we always we have to do a trade-off when we talk about model complexity in terms of polynomial functions, that higher degree polynomial versus lower degree, or in general, so many features with less number of features. Is a trade-off. When a model complexity is low, you get high bias, but the low variance. When the model complexity is high, we got the low bias. Error is low. Train error is low, but the variance would be very high. So at a point where we get this, this is a point where test error is decreasing, train error is also decreasing. But after this point, our test error is increasing. We should stop, and that point, that model complexity we should consider. This is what we can achieve maximum with the given training data set, with the given number of features, and with the given algorithm, we can achieve the best. This is a point you can understand this curve and interpret this curve like that. Okay, so yeah, there are other ways of handling overfitting, more mathematical way of handling overfitting. One is I said, okay, maybe select the features or come up with reduce the feature importance or feature selection technique can be used. Or one heuristic says that your data points should be multiple of parameter, say 5 to 10 times parameters. Parameters, that means features. With every feature, we have the one parameters. We don't want to restrict this relation. This is just a experimental, somebody has found out that your model will not overfit if your training examples are 5 to 10 times the number of features that you have. So if you have say 10 features, say maybe 100, 10 into 10 times, maybe you have 100 training example and so on. But this is not a good way of handling the overfitting. We don't want to have that restriction on number of features or the number of training examples. So we can automatically control the complexity of the hypothesis with something known as a regularization. Again, very important topic. We are learning with respect to linear regression, but it is applicable to any algorithm. There are regularization technique even for classification, even for regression, even for neural network, etc. Maybe one or two more regularization techniques would be there, but this concept is very, very common for all ML algorithm. It generally does what? It penalizes the large values of the parameters, but keeping all the features. We don't want to do feature selection. We want to keep all the features because all features are some or other ways contributing. Maybe few percentage only, but they're contributing in the prediction. Want to retain all the features, then how can we handle this overfitting? So penalize a large value of theta, and that we can do it by changing our cost function or a loss function. But what you need to understand, regularization is a modification to reduce the generalization error, but not the training error. So with the regularization, it won't have an effect on training error. It won't touch the training error, but it will give us a good generalization performance. Its goal is to reduce the generalization error. So what is that? So mathematically, this is the regression problem. So this is our regression loss function. We are adding some another quantity over here, lambda, summation of all the theta square. But important is starting from 1. So this is what theta j square. We are not penalizing that. That's important thing to remember. Rest of the features, coefficients we are adding. Multiplying with a constant lambda. So that lambda is known as a regularization parameter. It is got some value greater than 0. And this lambda is we discussed with respect to linear regression. Yes. Learning rate. This is another hyperparameter, lambda, which is a regularization constant. Now, what is important of this regularization term? It governs the importance of the term, like which feature, it controls the parameter values for every feature. Mathematically, I'll show you how. Now we are changing the cost function. That means our gradient update rule will change, but the gradient update rule will not change for the theta 0. So new value of theta 0 is still old value of theta 0 minus alpha. This is our learning rate. And 1 by n, this is what is prediction minus actual. So it's not changing. For rest of the thetas, rest of the features coefficient, we are adding this lambda into theta j. Now there is a mathematical derivation how we come to this point, but we'll not go in the detail of that derivation. But say our gradient update rule in a gradient descent, for rest of the thetas are coming like this. Now you can see this is the original gradient update rule. You can just check with the previous slide. Learning rate 1 by n is the average, and we are summing for all trading example. Prediction minus actual multiplied by that feature value. This is the original gradient update rule. Now, due to this regularization parameter, we are adding this lambda theta j, but it is in the bracket. So we simple open this bracket and rearrange. When we are rearranging, now we have got just two terms, second term and the first term. What do you observe in this? Compare it first with the original gradient descent without the regularization added. Whether the second term is the same as the original gradient descent.
Yes.
Okay. Now what is the first term? So original gradient descent says that nu is equal to theta old minus this alpha by 1 by n so on. So rather than this is new, this is old, plus we are multiplying some number to this old. Mathematically try to understand what is we are doing. This number is less than 1, some fraction. We also call this as a weight decay. In gradient rule, we are reducing the old theta value. We are controlling the old theta value before the updation. That's what is happening in case of regularization. And how this lambda helps, now you think about this lambda. We have theta j 1 minus alpha lambda by n. What happens if this lambda value is very high?
Go to negative.
Lambda value is
1
very
minus.
high.
Okay. The 1 minus this thing. So if
So
it's
this
very high,
term,
it will be the reduced.
this
new
effect
value.
will be so much reduced. Yeah, weight decay will be higher. This value will be reduced. Old value itself will reduce further. So that's what happened. If we have a lambda very high value, that means we are retaining. So you can say a number multiplied by say some number multiplied by say 0.003 or multiplied by 0.3. Definitely this value will be higher compared to this value. So when the lambda which is there in the numerator, if it is very high value, much the old theta value. So this way, this regularization term is controlling that how much the old theta values we are retaining or reducing. So that's what is the effect of this lambda. If it is too high, that means we are so much reducing the old theta value. It might happen that in certain value of lambda, all our thetas will become 0. Old theta value will become 0. We are not penalizing theta 0. So we are not touching that. If lambda value is too high. If it is too low, so this lambda is too low, this will become a very high number. We are retaining the original model. So again, its original is a complex model and we are retaining that. So the correct value of lambda is very important, which is between too high and too low. That means if we take the correct value, we are reducing the complexity. At the same time, retaining the old theta values. We are not making all of them as 0. That is what is where this regularization parameter lambda is important and it plays a part. That's why it's a hyperparameter. There is no fixed way to tell that which is a good value of lambda. So there are different hyperparameter tuning techniques. Simple, trial and error. Use one lambda value, check your performance, another lambda value, check your performance, and so on. So that's trial and error method. And that way we can control the overfitting. And if you look at this formula, what we are adding in the cost function is lambda multiplied summation of all the parameter value. But here square of all the parameter value. So whenever we take this square, this is nothing but a L2 norm. This is nothing but the L2 norm of the vector. So sometimes this is known as a ridge regression or L2 regularization. The name given, you might have heard this ridge regression, lasso regression. So this is the ridge regression or L2 regularization added to a linear regression. Now, if I change this, rather than a square, if we use simple absolute term, this is the L1 norm of a vector, and the name given to this is a lasso regression. That means we are applying a L1 regularization to the linear regression cost function. And again, it will affect our gradient update rule. Will not get into derivation. What term will get added when we use this L1 regularization? This is a term which gets added in the weight update rule. Alpha into lambda sine of theta j. So this is the sine of value. And luckily, we don't write all these equations when we implement it. In sklearn, it gives us which regularization you want to use, L1, L2, ridge, lasso. So we have separate terms. But this is for understanding purpose. Why regularization is used? So you can justify why it is used. And what L1, what is L1, what is L2, what is ridge? So ridge is L2 and lasso is L1 regularization. We are changing the cost function, adding the regularization parameter, which is used to control the values of theta. When we control the values of theta, indirectly we are controlling the importance of those corresponding features. Remember, each theta is associated with each of the parameters. This entire quantity. So I'm controlling the features. So mathematically, by adding the regularization, we are controlling the feature dominance on the output. And this is totally automatic process. We cannot understand, we cannot find out what is the correct value of this alpha. Only by trial and error, we can find the correct value of this constant. And then we use it for our deployment. Now there is a third regularization elastic net, a simple mathematical convenience again we will use, where we are combining L2 and we are combining this L1. But some L2, some L1, how much L2, how much L1 regularization we want to add to our cost function, that we are controlling with this mix ration R. So if R is 1, say I put R equal to 1, so this term will become 0. So when R is 1, this will become like a L2 regularization. When R is 0, so this entire term will become 0 and our L1 will stay. So you can just check mathematically, it's some constant which will help us that how much L2 you want to, L2 regularization you want to add to a cost function, how much L1 want to add. So elastic net is a combination of L2 and L1 both, and how much that proportion can be controlled by another constant R. Again, you can think about this as a hyperparameter. You don't know that you want to have how much L2 and how much L1. So we'll do with the trial and error. And then, okay, we can have 40% of L2, maybe 60% of L1, like that. All of this mathematically we are changing in a cost function. Remember, any changes in the cost function will change the gradient update rule. So for L1 and L2, this new gradient update rules are written here. In this case, derivation is not required. How it is coming. But yes, if you want to know, you can sit with pen and paper, take a partial derivative, and then you can confirm whether this final answers are coming or not.
One question
Yes, yes,
on the same slide which you just had open.
previous one.
Yes.
Yeah.
Not this one, previous one where we first applied that. One more, please. Yes, this one. So here, after applying this regularization, we are multiplying it with a smaller number of with on theta j, right? In the last line. So
Hmm.
we are kind of speeding up the reduction of the theta j value here, which is anyway going to happen, right? Maybe in more number of iterations. So is it just about speeding up the reduction of the theta j value?
See, you don't look at like that speeding up. What are we doing here? Before the weight update, we want to control the old theta value itself because they are very high. When the number of theta parameter values would be very high, so say I have a very high value of theta 1, this value will become very high. The
Right.
importance of this x1, dominance of x1 will become very high. If that is happening with every features, so that's very too complex model. I want to reduce the, say I have x1, x2, and so on, so many features, okay? I don't know, we cannot control which individually I can, control, which feature I can reduce importance, which feature I can increase. But with this method, what I can do, I can reduce this values. When I reduce the theta 1 values, indirectly that multiplied this entire effect of theta 1 x1 will be reduced. That's what I'm trying to do over here. And how am I doing it here? In a weight update rule, see the new rule, the new update will only happen based on the old theta value. If the old theta value itself is very high, so how much we will reduce? If you want to reduce it, then the gradient update rule. So we are reducing the old theta value itself first, and then applying a gradient update. So you want to relate it with the speed up, but then you are want to saying that okay, ultimately I may reach to that level if I increase the number of iteration. That you are not sure. This is not exact calculation that you can control on every iteration for every feature. Maybe for 2 features and 10 example, you can see with pen and paper and you can check what is happening. These are the general method which are developed when we have so many number of features and so many training examples. So in that case, this is a very short way of reducing the old theta value itself before the weight update rule. And then you don't have to think about it. Okay, if I increase the number of iteration, but then again, how many iteration you will increase? Sometimes a number of iteration increase, it might reduce too much. So think about that way. It may be doing speeding up. Yeah, as you're saying, it is actually speeding up the reduction of theta. On minus value of theta or plus value of theta. So all those things we don't know. We are talking about a lot of data and a lot of iterations. Okay.
So after doing these lambda, like trial and error of lambda values, will it not affect the target
No, it won't affect the
value?
No, it won't affect.
Because we are based on the feature, we will either increase the lambda value or decrease the lambda value. So
No, we are not doing based on features. See, we cannot find out that every feature, how much I should, parameter value should increase or it should decrease. So lambda is overall effect it is giving us that, okay, and we cannot do this handcrafted values. So it's only trial and error method. And it won't affect the target because the original problem was overfitting that we are trying to reduce. Our predictions were too perfect. That's why only you're doing, otherwise why will you add the regularization term? To reduce that too much perfection we want to reduce during the training. So are you getting a point? See, the original objective of regularization is to reduce the overfitting. What is overfitting? During the training, we have come up with the too perfect model where cost for our So our sum of the y values, some of the predictions we want not to be correct. And that's why we are doing this regularization. We want to reduce the overfitting. So that's why the control this lambda has come. If we too much reduce overfitting, we get into underfitting. If lambda value is too high over here, correct? It will definitely affect y, but we want to do that. That's our objective. I hope it is clear now.
Yes. Yes, ma'am.
Madam, one thing we can assume that like overfitting means the coefficients are very high.
Coefficients are high, not necessarily. It could be coefficients can have a negative. See, that depends upon every feature's correlation with the output value. If feature and output value are negatively correlated, then their parameter value will go in the negative direction. Right? So I cannot say high, very high, but if the feature and the output value is inversely correlated, it could go high in a negative direction. I mean, very low. The feature value could be very low. So that's why we have to find out feature correlation between every feature and every output, and then try to do that analysis. Why to do that? We have this direct method. Okay, so this is just L1 and L2, when to use lasso, when to use ridge. L1 regularization can make some coefficient to 0 because this is absolute value nature. It can actually perform feature selection. So L1 is inbuilt method in the during the model training, which will automatically perform the feature selection by eliminating the feature itself. But we want to use L2 because we don't want to eliminate all the features. We may want to reduce their coefficient values to very low value. If it's a positive coefficient, if it's a negative coefficient, we want to increase its value. So you look at both the direction, positive direction and negative direction of theta. Theta can have positive values also, negative values also. So we can use L2. So that's L1 and L2. In practice, people use L1, L2, elastic net and check which one is giving the best performance. But this is a theoretical explanation that what L1 feature. When you want to make sure that you don't want to eliminate any features, use L2. Okay, now this is one problem again for your practice, and last class also there was one problem. I had asked you to actually solve with pen and paper, and this is some values are changed. So please do so, and I hope you got time to solve that last problem. Gradient descent.
Yeah, we did.
You do that at least before the exam, solve it. So if you've got any doubt, you can ask me.
One question I had on that problem. So in that problem, we were running the iteration on all the training examples, right? N equals to 3. So in that sense, that becomes an example of batch iteration, right? Because we are taking all the training
All,
examples
yeah,
in a single
yeah.
run.
Yes, it becomes batch.
Yeah, if we take N equals to 1, like find the best values on one training example and then go to second, then it becomes stochastic, right?
Stochastic, correct. But here we are taking some, so it becomes all. I think here it is asked exercise, it's not mentioned. Okay, anyway, just solve this at least before the last exam, solve this, okay? Before the exam, before the last class, you solve this and ask me. Yeah, I have not got time, but anyway, I have to get the time before the exams. Okay, so I'll start with classification now if your regression problem is over. We have 30 minutes, so I can at least start some of the things. See, what we can do is, if whenever you have not understood, so go through all the recording in January 1st week and 2nd week before the exams. When do you have exam? I guess 15th, right? Some 14, 15 you have exam, or after that? Mid-semester exams.
18, ma'am.
18, yeah. So first 2 weeks, or maybe before the exam, anytime on the weekday, I can take your class for any doubt solving. So any morning time or evening time, 7 to 9, or morning 8 to 10. So that way it will help. But you have to go through the recordings, you have to practice on your own to understand. And I can take classes extra on weekdays because weekends you all are very busy. So for extra doubt solving classes, I can take on weekdays. But you have to first go through and do some practice on your own. Otherwise, you don't know what is happening, anything.
Ma'am, can you give us
Hmm.
some sample, like, practice problems to do at home?
See, we will do it last semester problem, question paper, we'll upload it for the exam. Now, we don't have such questions. I can create many problems on that, right? Then use the batch, like someone just said, 320 example, use a batch. I can say, okay, use a stochastic gradient descent, then you should know, okay, I should use only one training example, 3 iterations. So during one iteration, only one training example. So combine those concepts and you can create it. Otherwise, there's no question pool available. Even I'll simply change the numbers and give you, which you can do on your own.
Sure, ma'am.
So whatever problems are given in the slides, do it thoroughly with pen and paper. So I'm not explaining every steps. We are also giving you some steps in the slide. Do it and ask me if you're not matching your answer. Otherwise, you won't be able to solve in the exam.
And in exams, we will have
Hmm.
these kind of problem solving questions only, like
Some conceptual questions will come. Some problem solving will come.
descriptive.
So for not descriptive, no, not directly descriptive, no.
Okay.
So we'll give you the previous semester papers, so you will get an idea.
So in the previous example only, ma'am, it was mentioned during the problem that you only perform one iteration, but practically in realistic scenario, the program is going to go over on loop until it finds the best values where the loss is zero,
Yes.
or at least less than
Yes.
epsilon, right?
Yes, yes, yes. So
Okay.
today I'll show a demo. So I thought let the webinar get over. The webinar also they'll show you linear regression and all those things. Then I'll show linear regression, logistic regression all together, both the code. But I thought if you learn something in webinar, that will be good. Your webinars are done. How many? One should have been done by now.
Yet to be done on Thursday, coming Thursday.
Okay, that is the first webinar, correct?
Yes.
Demo. First, let's complete the theory so you can relate it with the whatever is done in webinar. And if you see the webinar, and then when you come back to the class, it will be easier for me. We can do it quicker than demo. Okay. So I'll start with the classification. I'll show you linear regression and all those demo later. Just before your exam, I'll show everything. Okay, so we are here. We'll talk completely different concept of classification, where our output is a discrete valued output. Say either 1 and 0 or 1, 2, 3, 4, 5, depending upon. If it is just yes and no kind of classification, that means either 0 or 1 kind of classification, we call it what? Binary classification. If it is, say, maybe yes, no, or say maybe, then I can define my classes like 1, 2, 3. Then it is known as a multi-class classification problem. We'll first talk about binary classification because there's a little change the way we the class classification. But before that, decision theory. What are the probabilistic generative models, discriminative models, and discriminate function? Some theory about this. Then the next algorithm is a logistic regression algorithm, which is the classification algorithm. But the name says it's a regression because it uses a regression function to perform the classification. So that's the name. Again, we'll define cost function. So it's a classification problem. We'll define the hypothesis function for this. Then cost function. Same gradient descent. I'll not explain what is gradient descent. And then we'll talk about multi-class classification. So this will be done very fast. Now you know the entire context of optimization and what is cost function, what is hypothesis function. Okay, first, before some decision theory. What is this decision theory? How will it help? This probability theory is very important. Why are you learning ISM course? Why are you learning probability so in detail? because it's very, very important in our machine learning, deep learning, or natural language processing algorithms. It helps in quantifying and manipulating uncertainty, that we know. And our predictive algorithms all are based on the uncertainty. We cannot say always 100% that our predictions are going to be correct. So that the probability theory plays a very important role over here. So we use a probability theory to quantify this uncertainty, and then we use a decision theory to make a decision based on this uncertainty. So that's why decision theory helps us. So what we want to do, predict the t, that is our target variable, given a new value of x. This is a goal. Training is done. Now it comes to make a decision. So when the new value of features come, some new unseen data set comes, we want to give a prediction. Say you are developing a portal for a housing real estate portal, and you are incorporating deploying some AI component into that e-commerce portal. And you are asking your clients or customers that add all the feature values. What do you want? How many bedroom, how many square foot size, which floor, which area, etc. So the user will enter all of these features that user wants, and you want to predict how much it will cost you. This so and so type of the house will cost you how much. That's what is the actual prediction. That's what is the actual use case of your model. So your goal is to predict that time for a given value of x. And this is entirely is an uncertainty based model. So indirectly, we want to find the joint probability distribution of x and t. Now I want to ask, have you come across this probability distributions in your ISM? Yes. Or a joint probability, a conditional probability, Bayes rule?
You're going through that.
Not yet, ma'am. We'll come through the Bayes rule.
Okay, but joint probability and conditional probability?
Yes.
Oh, that you know, right? For the formula you know.
Yeah.
Okay, fine. Now distribution, concept of distribution, have you come across? No. Okay. You can say this is the joint probability distribution. When we have so many values, we call it distribution. It's a single value, random variable having a single value. We calculate its probability. That's a difference right now. We will understand more of distribution in your ISM. So joint probability, Now say we have this classification problem we are dealing. This is our example data set. We have features, one feature, second feature, third feature, fourth feature, fifth feature, and sixth feature. And we want to say we have a target variable t, enjoy sport, and it has got three possible distinct values, yes, no, and maybe. So it's a multi-class classification problem. Okay. This is how our classification data set will look like. Another example of binary classification. Say we have one feature CGPA, another feature IQ, and then we have a job offer with so many CGPA, with so many IQ level, whether person is offered a job or no. So this is a yes or no kind of answer. Target variable we want output to be. It's a binary classification problem. And now here in this case, you can see we have IQ column with some different values and CGPA with some different scale. So we have got the scaled IQ. So we don't consider this original IQ into the feature. When we scale it, we just consider the scale value as one of the feature. So that's what data transformation is needed before we give this data set to the machine learning algorithms. Just an example. And say here pre-processing that we have done is min-max normalization. Some scaling we have done, feature scaling, and then we have normalized this feature IQ. And we use only that feature, not the original one, for a prediction task. Now, suppose the same CGPA, one feature, IQ, second feature, job offered is T. Rather than this 1 and 0, whether a person is offered a job or no, we get an output in terms of a probability, whether a job offered is 1 or not. So you can see these are all the values of probabilities, say 0.8. That means it's a 0.8, 80% probability that a person having a CGPA of 5.5, IQ of 6.7 can be offered a job. So algorithms which gives output in the terms of a probability. Many algorithms gives us output in the system. Logistic regression gives us output in terms of a probability. Naive Bayes gives us output in terms of probability. Even neural network gives us output in the form of probability. So there comes your understanding of probability theory should be very clear. Okay, so now we are getting this probability. So how do we write this in a probabilistic term? We have got a certain set of features and we have got a class. In this case, K is 0 and 1. That means class 1 and class 2. Okay, let's put it 1 and 2. It doesn't matter whether you use. So it is class 1 and class 2. So given a joint probability of a certain features and a class. So say for the first example, we have a certain set of features and say class C1. For a second, we have say certain set of features and class C2. Say it's second class. Then we have third. We have a certain set of feature values and a class 1 and so on. So in general, we say we are interested in finding out the joint probability distribution of the feature values for all training examples and their corresponding class. Now there's a relation between, this formula. Does it look similar or familiar?
Yes, ma'am.
This is a
Yes.
conditional probability given by joint and marginal probability. So this is where either you talk in terms of joint probability or we can talk in terms of conditional probability, because in our machine learning problem, this denominator doesn't matter. So many times you see whether we are talking in this joint probability corresponding class. That probability is what we are interested into. Okay, now comes the Bayes rule. It's a Bayes theorem, and there is a formula for the Bayes theorem. Given input features and the corresponding class value. So suppose I have a C1 class, I will write down something like this. And if we have a C2 class, we'll have another quantity. So per class probabilities we will get. For a C1 class, one value, for C2 class, one value. Apply this formula. Now you will learn more in detail in your probability. What is this formula? This we call as a likelihood. This we call it as a prior. And the denominator is a marginal probability. But anyway, we are not interested into the denominator, marginal probability in terms of the probability theory. Likelihood, what is a likelihood? Again, we will talk about this in machine learning as well and in your probability. So I'll not tell what is this likelihood right now. But say what you see in terms of a probability formula, there's some conditional probability, right? So, yeah, so here only I'll write down. Say I'm interested in finding out the C2 class probability. Probability of features conditioned on the C2 multiplied by the prior probability of C2 upon P of X. So what is this prior? Whether for every class there is a prior. Probability that a person enjoys sport irrespective of days of weather condition. So this is a probability that person will always enjoy the sport. There is no X. If a very sporty person doesn't care about the weather, but he will always enjoy the sport. So that is known as a prior without the existence of the features. What example, it's enjoy sport. C1 is a enjoy sport. C1 class is what is enjoy sport. And C2 class is not enjoy sport. So probability of C1 that person will always enjoy the sport. We call it as a prior, but if that probability, can that probability change? Features are incorporated. That means if the weather conditions are incorporated, whether that probability will change or not. That means we are changing this prior based on this Bayes rule. And that's what we call it posterior probability. Never mind if you do not understand so much over here, you will have a lot of chances to understand this Bayes rule again in your ISM class and even machine learning as well. But for the time being, understand there's a posterior probability we can calculate, which is likelihood multiplied by prior dividing upon marginal probability. Where prior probability is, we don't have any data set. But we know a person will always, there are certain set of people will always enjoy sport. But that is just our assumption. It might change if we incorporate the features. Here, what are the features? Weather condition. If we incorporate a particular weather condition, the person's probability of enjoy sport might change. So that is what Bayes rule will help us in modifying our prior. So that's why we call it, when we modify the prior using this formula, we call it posterior probability. And this is what is a probability that we are interested into in our machine learning. So here, the probability which is coming here in the last column is nothing but the posterior probability. And there are many algorithms which gives us this posterior probability in a different way. So the first algorithm that we will see how we get this posterior probability using logistic regression. Okay, so now going back to our decision theory. Why we are learning this decision theory? Because we want to minimize the assigning our input features to the wrong class. So that's the reason that we are interested into learning the probability. If higher the probability, see here, why this we are assigning a 1 class? Because we know that, okay, the probability is high, so we are assigning 1. If a probability is 0, not 0, if a probability is less, we are assigning 0. The question comes, how much high, how much low? So there has But for the time being assigned, decision theory will help us. For high probability, we are making a decision of assigning 1. For low probability, we are making a decision of assigning 0 class. That means yes or no. Whether a person will enjoy sport or person will not enjoy sport. So say, now try to relate with this classification, same example, CGP IQ problem. So we have this learning algorithm. Apply any learning algorithm, maybe logistic regression, maybe naive Bayes, or maybe neural network, logistic regression, or the naive Bayes algorithm. You will learn all this in this course. Then the model is actually finding out this probability, the joint probability, whether job is 1 or job is 0, whether a person will get a job with having so and so qualities in terms of features, or a person will not be offered a job with so and so quality offered. And then we want to apply this model for our test data. That means that's where we will perform the decision. Whether to apply, whether to write a 1, 0, 0 or to write 0, 0, 1 or what. If a person comes with some new qualities. So that's where you can link it with how the decision theory and the probability theory are helping in our classification problem. Now we have to understand this in terms of distribution. Okay, before that, you don't know what is a distribution concept, right? You know what is a random variable?
No.
In your probability, it is not it started with a random variable concept. Okay. I don't know. Say you have a random variable X, say height of a people in India. Random variable, that means that variable can take any value. Now, say we have this is a population of India. So many people here, and people can take a different height. So I have say X1, one person's height. This is not a feature, okay? This is just a height. So one person can take a height of 5.3. Another person can take a height of this. Another person can take a height of 5.4 and so on. So we try to plot, say, random variable x, and on a y-axis, what is a probability that this random variable x can take some value. In this example, that what is the probability that a person's height could be 5.3, 5.333, 5.43 and so on. So we have such, now we cannot do this for entire population of India. So we take a survey, we take a certain people of India, certain geographical we cover, and we take a different values of x. Okay, a person can take a value of say so and so value of a height over here. Second person can take so and so value of here. Maybe third person can is height here. The fourth person could be height here, and so on. And we try to plot the probabilities value like this. So we call this as a probability distribution, and on the on the y-axis, this is a probability density function. It's PDF. It's a probability distribution function. It's simple that what individual person in our sample, what is the probability of their height? And then we try to plot a graph. So this is known as a probability distribution curve. Probability distribution curve. What example I have taken is a normal or Gaussian. Sometimes it is also known as a Gaussian distribution. There are so many such distributions possible. That's what you will learn in your probability class. Just taking an example of a normal distribution, which is for a continuous data. Height is a continuous data type. It's not a discrete data type. So that's a probability distribution I'm talking about. Now here, rather than height, what do we have? Say CGPA. So CGPA can take many values. So we can have for all values when we plot and try to draw the graph, which is passing through all the values, we are getting this kind of a graph. Is one graph for, say, the blue is a graph where we have drawn that graph using the points where our target variable is 1. The class is 1. Then we are plotting. So we are separating our data points, or class 1 points together, all class 0 points together. And then we are plotting this blue curve. It's a probability distribution curve. And then we are taking all the data points of class C2 together. Point all the points, we're getting this green curve. So this is a probability distribution curve for the class, say C2 class. Okay, this is a C1 curve, and this is the C2 curve, green one. And now just this is what is understanding of probability curve. You can say rather than height on x-axis, I have written CGPA, and on the y-axis, it's a PDF. This is a PDF. So CGPA is another random variable, height is another random variable. Now coming back to a machine learning problem, say I want to predict, our model is predicting if a CGPA 7 is a cutoff. Anybody having CGPA less than 7 belong to class C1, or anybody having CGPA less than, greater than 7 belongs to class green. That's what my model is predicting. That CGPA is greater than 7, then class C2. And if CGPA is less than 7, then class C1. That's our model's prediction. We don't know if it's accurate or not. So you can see this, the red line is what is the decision threshold. So here, let's say this is the decision threshold for any such random variable. And say we have this probability, the blue curve, the first curve belongs to C1 class, where given a feature and the corresponding prediction C1. So what we did over here, we collected all the one values. So it's a multi-dimensional, you can visualize. So this is a curve which shows a joint probability distribution of X and C1. X are features, C1 is one class. And the second curve, this one, which is a simple normal curve, bell-shaped curve, when it is giving us the probability distribution of X, comma, C2. That means joint probability distribution of X and C2. Based on, and then this is what is plotted, and we have this decision threshold. Whether we have to choose whether this decision threshold is correct or not. It's a prediction. Our model is giving us that prediction. It's a X hat. So you can just look at it. Green, red, and blue are the regions of error. Can you understand why those are the regions of error? Here, on the right-hand side of my threshold is a C2 class. That's what my model is predicting. And left-hand side is a C1 class. That's what my model is predicting. Now I'm making a statement. Green, blue, and pink. Those are the error regions. Model is making the error. Is it making any... Is it correct? I'm saying those are the error regions. Is it correct?
Yes, ma'am.
See here, you have to read these two statements. If X is less than X bar, the actual values, so this is the actual value, is less than the predicted values. Errors are represented by some of the red and green regions. Is this correct? This is a threshold of X bar. So what my model will predict, anything on the left-hand side of the threshold, model will predict C1. So the red and green regions are the error due to points from where class C2 is being misclassified as C1. The model is predicting as per my threshold, they belong to C1, but you can see the pink part, I mean red part and the green part actually belongs to C2. They also belong to C1. Let's not talk about it right now. Suppose the data points, they are belonging to C2, but because of our threshold, our model is predicting them as C1. So red and green are the error for the class C2. Similarly, when actual X is C1 class, because as per the threshold, our model is predicting them as a C2 class. But you can see this blue region is part of the C1. So this is the region for the error. This is the region of the error for the C1 class. Belongs to the region R1. R1 is nothing but all the points belonging to C1. So this is the R1 region and the second curve is the R2 region. The point belongs to R1 region but classified as C2, or the point belongs to the R2 region but classified as C1. So what is that probability? That this is what is happening. That is being mathematically written like this. It's integration over the region R1. That particular point is being classified as C2, but that point belongs to the R1 region. So this is the mathematical understanding and interpretation. And that's what is a probability of a mistake or a probability of a misclassification. It's just a theory, so try to understand this theory. And then what happens? If we move this X bar, we try to move this threshold and get to this optimal threshold point, X0. So just pay attention to this X0. If you're moving X bar to X0, can we reduce any error? Not necessarily all the errors, but what are we reducing at X0?
C1
red-
plus error.
We are reducing the errors.
Pink
The red
part.
part is completely going away, right?
Yeah.
It's a correct. So we cannot reduce all the errors, But when I say we are getting rid of this red part, the error region, that means we are reducing the error for C1 class. Oh, sorry, we are reducing the error for the C2 class, because this red portion was the part of the C2 which was misclassified as C1. So we are getting rid of red class. So at least some error we are reducing. Still we have blues and greens. Can we just move threshold anywhere else that we can get rid of blues and reds? No. So this X0, you can even think about it. So this X0 is an optimal threshold point where we are getting a minimum error. We will still get some error, but further error reduction region and R2 region are overlapping region. And the regions are not necessarily always you will get this kind of curve, but this particular data set, when we are plotting this curve, for this X0 is the optimal threshold that we are getting. And how can we get this optimal threshold? So mathematically, when we write this equation, that some data point belonging to R1 but classified as C2. So we want to reduce this probability. At the same time, we also want to reduce this probability. A data point belongs to R2 region but classified as C1. So we want to reduce that probability. So we want to reduce either of this or both of this for both the classes. So indirectly, we are now concentrating on this joint probability. Probability of XC1, XC1 and probability of XC2. So if X point belongs to R1, then this probability should be more or less. Yes. A simple question. When a point X belongs to R1 region, R1 curve. This is the R1 curve. And the second curve is the R2 curve. This probability should be high. If a point X belongs to R1 region, then that point being classified as C1, we want that high probability, compared to if the X belongs to R1 belonging to C2. We want this probability to be low. This joint probability of X and C1 is high. We want if the point belongs to R1 region. If point, or I can say X belongs to, I can write mathematically R1 region. So now what is this? We can apply the Bayes rule. So this joint probability we can easily get by multiplying this marginal probability and this posterior probability. Just get rid of the denominator. So both the side we can get rid of this. Mathematically, this we want P of joint probability C1 greater than joint probability of X and C2. I'm simply writing this formula. So indirectly, we want the posterior probability of C1 given X greater than the posterior probability of C2X. And this posterior probability we can get using the Bayes rule. So Bayes rule will give us the optimal decision boundary, and that we can get this optimal decision boundary how? By comparing this probabilities. The posterior probability. So I started with this probability, X belonging to R1 region and classified as C1. That's what we want. X belonging to R1 region but classified as C2. We don't want that. So we want to reduce this probability and increase the probability left hand side. Indirectly, we are comparing their posterior probabilities. So this is what this decision theory is trying to help us. First calculate the probability, then compare the probability and make a decision. Whichever, so now I have to make a decision. So during all this various algorithm will give us this two class probabilities. How do we do a comparison? Whichever is higher probability, we will denote that class. Here the C1 class probability is higher, then our prediction will tell that this data to C1 class. So before making that, why are we making that prediction? That whichever class probability is higher, that we will assign that class to that data point. That root lies on this minimum misclassification rate or a decision theory. So that's the basis of the classification, any classification algorithm, that when we compare the probabilities, whichever class probability is higher will assign the target label to that class, whether it's C1 or C2. Why it is correct? Because there is a Bayesian justification to that. This Bayesian justification is very, very important. Lot of places this Bayesian justification will come. We'll talk about Bayesian justification in detail post mid-semester. By that time, you'll be clear with your probability concept. Here, just to understand decision theory, to understand minimum misclassification rate, that Bayesian justification or Bayesian theory helps us to get this minimum misclassification rate. That means this is an optimal decision boundary we will get based on the probability theory. We are getting this decision boundary. We cannot reduce error further. This is the theory about this decision theory. And this is explained in Christopher Bishop's book. So if you want to go in detail. Okay, so I will end it over here. And next class, I'll continue. Still, this probabilistic algorithm, generative algorithm, what is discriminative algorithm, and like that. So,
Ma'am, this PPT would be uploaded in Taxila, right?
see where I'm uploading, Takshila, all the common PPTs are uploading. I'm annotating over here. So I'm updating where? You all not aware where I'm updating?
Yeah, in Teams, right?
In the Teams, yeah, in the Teams.
Okay.
I'll show you. Here in the files, and here I upload. It will come. Class material, where you get your recording, class recording, there is a class material folder. Yeah. Here I upload everything. It should be visible. You can see. These are what I'm using in the class. So it's easier. Takshila is all what is a common slides, what for all section is getting uploaded. So you can see what is happening. So are you clear, right? These annotated slides are over here.
Yes, ma'am.
Okay. Any other doubt?
No, last time there was one example which you said we can discuss in the next class.
That's what I said, gradient descent. Did you solve it? I said first you solve it, then we will. I showed you that, right? In the
Yes,
beginning only
yes.
this. Did you solve that?
Yeah, I was trying to solve that. Yeah.
So we have shown that in the slide. Now you solve it and then we will discuss about it. Some steps already shown in the slides. Whatever are the missing steps, I want you to understand and solve it. First you solve with pen and paper and see what part you have not understood, that I will explain. Okay?
Okay, so can I ask one question?
Yeah, please do so.
Like I was, when we say that, that summation thing, I'm getting a little confused there,
Okay.
When we say sum of, 1 second, do you have that slide? I mean,
Problem slide.
yeah, problem slide.
1 minute.
Like we say that W1 dash, like W0 I was able to do. W1 dash, that sum of W0 plus W1 into X1 plus W2 X2 minus Y into X.
Here, you can see the slide, right?
Yeah.
So
Yeah,
what it is doing, this is the learning rate. Sorry, this is the
Yeah,
number of
this is
examples, 1 by 3. This is
examples,
okay.
then alpha.
Huh.
Then sum.
From this 5, yeah.
Yeah, this is right.
Hmm.
So W0, I got it.
It's given, right?
Yeah. This
So
I got
what is this
it.
0.03? It's given in the question.
It's given in the question, yes.
Yeah, and this BMI value you will take from here.
From
For
here.
first example 35, for second example 25, third example 30.
Yeah.
So first time we will make this equation for with we have what 3, right? No, only BMI and pressure. This two. So first equation
Yeah.
will be 5 minus what 0.0. That's what I said. You should be trying to do that on your own. This is 80
Yeah, I did that.
minus 0.03 multiplied by what? We have 35, correct?
Yeah.
35 minus what is corresponding RRCHID 1.81. 1.81.
1.81, yeah.
Huh. That is plus. Sum is there, right?
Yeah.
Plus 5 minus what is that? Next one is 0.03 multiplied by we have got 80 minus 0.03 multiplied by 25. The second example.
Yeah.
Minus we have 1.22 and then take the third one.
Yeah.
So that is what is sum. And then you calculate answer. That is a W0
Yes.
and then W1 and so on.
Yeah.
Okay, so just solve with
Yeah.
pen and paper, solve it and then show me when you are where
Yes.
you are getting. If you
Ma'am,
cannot
can
solve
we
this,
take a picture and post somewhere like for you to see it?
yeah, here itself you can do that. Or you can there is a discussion forum in Takshila where you all can put up your whatever your doubts you have, and there are TAs will answer, I'll answer, or some other student also can answer. You know that at Takshila we have a discussion forum.
Yeah.
There you can put, yeah, and discuss. TAs will also answer.
Okay, ma'am.
If I have not seen that, yeah.
Okay.
So discussion forums are for that. The general discussion we can do it, or other students who have seen, who have solved can answer. It's kind of a peer learning tool as well.
Sure, ma'am.
Okay. So we'll meet next class. I'll stop recording right now.
Ma'am, just one thing. Ma'am, I mean, this far I have attended almost every class of machine learning, but this one, this one I could not attend. I joined late, so I'll be watching the recording and
Yeah.
before going to the next class. But in the meantime, if I have any doubts, can I reach out to you in Teams or uh,
Actually, this 2 weeks would be difficult, but you just, if you've got any doubt, write. Teams, I don't see messages. Write an email.
Okay, ma'am. And one more thing, I have the Tom Mitchell book. Apart from that, do I need to, collect or buy any other books, or I know
Bishop.
that you have
Christopher
recommended.
Bishop.
Okay. Both the books are required, right?
Yeah. PDF are available. So right now we just go through with the PDF. Online PDF.
Yeah.
Take the online PDF right now.
Okay,
Freely available.
ma'am.
Okay. Thank you.
Yeah.